Welcome to another CSI analysis program. Here at CSI, we are seriously committed to the success of your reliability-based maintenance programs using predictive and other proactive maintenance methods. When diagnosing problems, spectral data gives a lot of information, but sometimes key elements are missing from the spectral data. Instead, these key elements are often found in waveform data. For this reason, it is extremely important for you, the analyst, to be able to use the waveform data to confirm or pinpoint the source of any problems. Applying the tips and techniques of this program, detailed waveform analysis, will enhance your RBM program, increasing uptime and saving thousands of maintenance and downtime dollars. Whether you use multi-channel analyzers or single-channel analyzers, a good understanding of waveform data and how it affects spectral data increases your ability to accurately determine the root cause of vibration, as well as the severity of any problems. This program reviews how a waveform is created and transformed into a spectrum, as well as the differences in the various waveform units. We will show how occurrences in a machine are reflected in the waveform and spectral data. Other topics include how to use waveform characteristics to distinguish certain faults. What is modulation and what does it tell you? How is modulation represented in spectral data? And how to collect the waveform that gives you the most information for a thorough analysis. In a previous program, Introduction to Vibration Analysis, we used an unbalanced tire to show how a waveform is simply a trace of a machine's movement over time. Notice that as the wheel turns 90 degrees, the trace also moves relative to the center line. A 90-degree rotation in the tire from the top corresponds to a movement in the trace from the top to the center line. Another 90 degrees is from the center line to the lowest point of travel. Another 90 degrees is from this lowest point back up to the center line. The final 90 degrees rotation of the tire moves the trace from the center line to the top point of travel. This angular relationship is called phase. It is important to understand this phase relationship as it will help us later in determining some waveform characteristics. Although this example traced a tire's rotation, we typically measure the back and forth movement due to the rotating mass. This vibration can be compared to the movement of a spring mass system. The up and down motion of this mass is similar to the directional vibration of a machine due to imperfections in the rotating mass. If a pin is mounted on the moving mass and paper is pulled past it, a trace of the movement is recorded on the paper. This trace is like the trace of the unbalanced tire. Let's look at the waveform generated from this motor that has an unbalanced condition. Notice that it is smooth and very repetitive with a sinusoidal shape. Since we know that one rotation is equal to one complete sine wave, we expect the time between two of these peaks to equal the time it takes for the rotor to turn once. When we place this phototack so that it sees a mark on the rotor, the speed is shown as 1756 RPM. This is 29.3 Hertz. This frequency can be calculated from the waveform using a method derived by a French physicist, Baron Jean-Baptiste Fourier, who lived from 1830 to 1928. Late in his life, he proposed that the complex waveform could be represented by the sum of individual sine waves and cosine waves of varying frequency and amplitude, and separated by their repetition rate to create a spectral view of the same data. In other words, each repeating sine wave could be separated, and the time for each cycle of the sine wave determines the discrete frequency of the sine wave. The process allows these individual waveforms to be viewed from the end at its discrete frequency, and is called a spectrum. Although Fourier was scorned for this concept, it was later proven accurate, and a modified method of his process was named in his honor. It is called the fast Fourier transformation. Thus, the common name for the spectrum is abbreviated to FFT. The mathematical conversion from a sine wave to the spectral view is done simply by dividing the time for one complete cycle into one. This obtains the inverse of the number. For this waveform, the time between the cycles is 34.2 milliseconds, or 0.0342 seconds. Dividing this number into 1 yields 29.3 cycles per second, or hertz. This value is displayed on an FFT plot as a frequency of 29.3 hertz, or 1756 cycles per minute. This spectral data is commonly used in vibration analysis to determine problems and the severity. However, recall that the Fourier transform is valid only on repeating sine waves and cosine waves. This means that some information may be in the waveform and not in the spectral data. It is important, therefore, to examine the waveform content as compared to the FFT. The waveform is really a continuous signal that the vibration sensor sees. But most of today's analyzers are digital units, which mean they use an analog to digital or AD conversion to manipulate and store the data. The analog signal then must be sampled with enough points to store a good representation of the actual waveform. This waveform is a stored digitized waveform. The actual stored points have been connected by lines, but the cursor only lands on the digitized stored points. Some machines generate a dominant frequency such as this, but most machines generate multiple frequencies. The effect of multiple frequencies can be seen using the single-channel analyzer, a CSI Model 2115 machinery analyzer. We will look at two independent signals, then combine them to demonstrate the effect of multiple waveforms. The first signal is from the same rotor kit with a dominant unbalanced condition. Notice that this is not a smooth sine wave, but has other energy riding on it. The second signal is from a signal generator. The input frequency is 20 Hz and is a smooth sinusoidal waveform. The two signals combined show the amplitude variations as the signals add and subtract from each other, creating a more complex time waveform. This example showed the waveform data in acceleration. In another program, Introduction to Vibration Analysis, we use go-karts to demonstrate that a waveform can show three precise measurements. The displacement measurement is the total distance traveled from one peak to another. The greatest speed or velocity is at the midpoint, and the greatest acceleration is at the turning points of the waveform as the direction changes. Each measurement of displacement, velocity, or acceleration can be displayed as a separate waveform simply by displaying the maximum velocity or acceleration at the top of the waveform. Remember that industry standards measure peak to peak on displacement waveforms, zero to peak on a velocity waveform, and the RMS value for an acceleration waveform. Earlier we pointed out that there is a 90-degree change from the zero line to the positive peak and 90 degrees from the zero line to the negative peak. When comparing the three waveforms, notice that the velocity waveform does not overlay the displacement waveform, but is ahead of it. The maximum velocity occurs 90 degrees before the maximum displacement occurs. Velocity is then said to lead displacement by 90 degrees, or that there is a 90-degree phase difference between velocity and displacement. The acceleration waveform leads the velocity waveform by 90 degrees. Maximum acceleration has a 90-degree phase difference from maximum velocity, and a 180-degree phase difference from maximum displacement. We'll use data from this small rotor kit that has an unbalanced condition to demonstrate this phase relationship. The phototac gives a constant reference signal as we display the incoming data from the sensor in the 3 units on this multi-channel analyzer, a CSI Model 2400 4-channel analyzer. The square wave on the screen is the reference signal from the phototac. One revolution is from one square wave to the next. The smooth sine wave is a displacement sine wave from the sensor. Notice how this displacement sine wave lines up with the square wave. The velocity waveform is now shown, and the relationship from the reference pulse is 90 degrees from the displacement waveform. With the acceleration waveform shown, notice the relationship to the reference signal. It is a full 180 degrees from the displacement waveform and 90 degrees from the velocity waveform. The concept of the phase relationship among the 3 waveforms is an important one to know, and can help you understand the necessity of using the same units throughout the procedure, such as a balance job. Let's compare the information the 3 waveforms tell us. This displacement waveform indicates an unbalanced condition in this machine. It is smooth and very sinusoidal, with no other energy apparent. The same measurement point and velocity still has a predominant 1 times sinusoidal waveform, but has other energy that could be multiples of turning speed. The acceleration waveform of the same point shows much more energy present with high-frequency energy. It is important to note that these 3 measurements are made from the same measurement point with the same measurement point setup. Since acceleration is directly proportional to force, as Newton's second law proves, the energy shown here is related to the force of any impacting that may be occurring in the machine. Since this impacting can be such a destructive force, it is usually best to store and examine the waveform in acceleration units to have the most information. Waveform energy is made up of multiple sine and cosine waves, which can be separated into individual frequencies using the fast Fourier transformation and displayed as a spectrum. Although the analyst can derive a lot of information from the spectral data, the waveform in acceleration can hold information that is not transferred to spectral data. In the previous section, we showed the importance of the waveform and the information it contains. We need to be aware, though, that the waveform may have limitations due to the limitations of the analyzer that can mask some critical problem. It is important to set up the measurement to obtain the information you need. We have pointed out that most of today's analyzers are digital and actually only store points that are then connected to show a representation of the actual waveform. If the analyzer stores 1,024 sample points for a particular waveform, it has twice the information that a 512 sample point waveform has for the same data. The importance of the number of sample points can be demonstrated using this analyzer to monitor a rotor kit. Setting the sample size to 1,024 points and monitoring the waveform, notice all the detail of the waveform with the energy showing random impacting. Now changing the number of sample points to 256 will have only 1/4 as many points in the waveform. Notice the waveform is fairly smooth without much indication of impacting. It is much more difficult to accurately determine the condition of the machine with this little information. The number of sample points is typically referred to as the waveform resolution. Some analyzers store a maximum of 1,024 points, while some have the capability to store more than 16,000 points for a waveform. For most routine analysis, 1,024 points provide the information needed to make an accurate diagnosis. With adequate waveform resolution, you will be able to pick out certain patterns in the waveform to determine whether the energy is periodic with repetitive energy, complex and varying, impacting with random or repeating spikes, or has discontinuities, or is asymmetrical and has truncation, whether there is influence from process or electrical frequencies, whether there are low-frequency events or modulation. Let's consider each of these waveform characteristics in detail and the effect it produces in the spectrum. The spectral data from this unbalanced rotor kit is a distinct peak at the frequency of the shaft speed. The peak is very narrow and does not have a wide skirt at the bottom. This indicates that the waveform is dominated by a single frequency. Viewing the waveform in displacement units, we see that it is indeed smooth, sinusoidal, and repetitive. The amplitude from peak to peak is the same as shown in the spectral data. The waveform in acceleration units is more complex due to the energy from high-frequency impacting riding on the 1 times sine wave due to the unbalance. But the waveform is still dominated by the single frequency due to the unbalance. Periodic repetitive waveforms can be at the turning speed of the shaft or its multiples. This motor generator set is misaligned, and the waveform is very repetitive, but not all the amplitude is the same. This is because there are actually 2 sine waves, with one of them being stronger than the other. We expect the spectral data to have 2 peaks then, with one being higher in amplitude than the other. Although these 2 examples show synchronous energy creating a periodic waveform, non-synchronous energy can also generate a periodic waveform. This waveform has a repetitive pattern, but appears much different than the previous examples. The vertical lines mark the shaft turning speed. Notice that there are 3 events that occur during some shaft revolutions, and 4 events in others. This indicates that although the source of this energy is repetitive, it is not synchronous or a harmonic of shaft turning speed. This is an example of energy generated from a non-synchronous bearing frequency or from another component in the machine which has a different shaft speed. This spectral data may appear to be very similar to the spectrum generated by a periodic signal because there are several multiples of turning speed present. A closer look reveals other information. These peaks have a wider base or skirt and are raised off the floor. This is not usually the case with very periodic energy. One look at the waveform and we see it is not anything like the waveform energy due to unbalance or misalignment. Instead, it is very complex and busy, with non-repeating or random impacting energy. This energy is from a looseness condition that is causing components to rattle against each other, creating many frequencies. A complex waveform may include many of the waveform characteristics discussed in this section, such as asymmetry and truncation or severe impacting. Recall that the fast Fourier transform process separates individual sine waves and displays them as discrete frequencies. With this much energy, there will usually be sine waves equal to the turning speed frequency as well as its harmonics. The remaining energy may add noise that includes all frequencies and therefore raises the base floor of the spectrum to some amplitude. An impact hammer is usually used for resonance testing, and the accelerometer response is measured to determine the resonant frequencies. In this case, however, we will only measure the instrumented force hammer and capture the energy of a single impact. A single impact imparts all the frequencies, but does not have any repetition. Remember that Fourier's basic premise states that the complex waveform is the sum of harmonics of the repetition rate. In an impact, there is no repetition rate, so this creates a problem. Energy occurs at all frequencies, and there is only one point in which they are all in phase to add together to produce the pulse shown in the waveform. The resulting spectrum does contain energy at all the frequencies, but no single dominant frequency. The net result is a continuous spectrum and is often referred to as a raised floor. Again, the waveform data has the most useful information. In acceleration, these impacts are proportional to the force. When 2 or more impacts occur, the waveform data shows each impact as we would expect. Each of these 3 impacts produces a single non-repeating pulse which imparts all frequencies and creates a continuous spectrum. However, since there are 3 impacts exciting all frequencies, these frequencies will be in and out of phase, adding and subtracting frequencies spaced at the repetition rate of the impacts. This waveform is from a blower that has an outer race defect on the bearing. It has severe impacting to plus and minus 7 Gs, but notice the pattern is very repetitive. When the waveform is expanded, we can mark one impact and move to another. The time between the impacts is about 18.5 milliseconds. This approximates a frequency of 54 Hz. The spectral data shows multiple peaks that have wide skirts. Setting the primary cursor on the peak at 54 Hz, we see that the harmonic cursors fall on top of the peaks. Although the impacts in the waveform are spaced at an interval equal to 54 Hz, the energy shows up as multiples of the frequency. This is due to the FFT process, which adds a series of sine waves that are exact multiples of the repetition rate of the signal creating the harmonics. To Fourier's credit, we can see that the transformation from the waveform to the spectrum reduced the complex time waveform to its individual sinusoids. In this case, the impacting is much more evident in the waveform, and its repetition produces harmonics in the spectral data. In a single impact, all frequencies are present, but because there is no repetition, there is no distinct frequency in the spectral data, but appears instead as a raised floor. Multiple random impacts also cause a raised floor and can generate harmonics of a frequency. This waveform is very unconventional and indicates specific conditions. Remember that this is a digitized waveform, and the stored information is actually dots. The lines simply connect the dots. This means that as the waveform data was being sampled, something changed abruptly in either the machine or the instrumentation. Data with discontinuity usually indicates a loss of the input signal. In this case, a sensor cable had broken, causing the intermittent